Section 7.3 is on logarithmic functions as inverses. The inverse of the exponential function y equals b to the x is x equals y to the b. Remember, we just switched the x's and y's. But in order to write this equation for y in terms of x, in other words, to solve x equals b to the y for y, we need to use something called a logarithm. We write this as y equals log base b of x, and that's how you read it. Y equals log base b of x. So here's a key point. So for b greater than 0 and b not equal to 1, log base b of x equals y if and only if b to the y equals x. In other words, I'm going to go ahead and outline this here. This is how you're going to turn something from a logarithmic equation, which is what we have here, into an exponential equation, and vice versa. We say that the y in the expression b to the y is the logarithm in the equation log base b of x equals y. The logarithm y is the exponent to which b must be raised in order to get x. So that means that y equals b to the x and y equals log base b of x are inverse functions. Let's take a look at a couple examples here. First, we need to write each exponential equation as a logarithmic equation. So remember, we're going to use the fact that log base b of x equals y can be written as b to the y equals x. So the base becomes the base. The y, what's on the other side of the equal sign, becomes the exponent, and the x is the solution. So here this is going to be log base 8 of 1 equals 0. Or in other words, 8 to the 0 power equals 1. For number 2, 4 to the third equals 64 is going to be written as log base 4 of 64 equals 3. Or in other words, what power does 4 have to be raised to equal 64? 4 to the third is 64. Let's take a look at a couple logarithms here that we need to solve. And this says find the value of each logarithm. Log base 16 of 64. Well, the first thing I'm going to do is turn that into an equation. Log base 16 of 64 equals x. Now I'm going to go the other direction and write this logarithmic equation as an exponential equation. So 16 to the x equals 64. Now in order to solve this, I'm going to write each of my bases in as small a base as possible. I know that 16 is 2 to the 4th, so 16 to the x is 2 to the 4th to the x, and 64 is 2 to the 6th. So since my bases are the same, I can just pull off the exponents and make those equal to each other. So 4x is equal to 6. I'm not really canceling the bases. I'm just saying that if the bases are the same, then the exponents are going to be equal to each other. So then x is equal to 3/2. You can check this by plugging it back into the exponential equation here. Grab your calculator. Is 16 to the 1.5 power equal to 64? And indeed it is. Let's do the same thing here with log base 2 of 1/4. So I'm going to rewrite that as log base 2 of 1/4 equals x. Now I'm going to turn that into an exponential equation. 2 to the x equals 1/4. And this one is already, 2 to the x is already written with a small base, but I can write 1/4 as 2 to the negative 2. So x is equal to negative 2. And again, to check that, plug that into the exponential equation. Is 2 to the negative 2 equal to 1/4? Indeed it is. Oops, hold on. There we go. A common logarithm is a logarithm that has a base of 10. We can write log base 10 of x as just log of x. The base of 10 is implied. Because exponential functions and logarithmic functions are inverses of each other, The graphs of y equals 10 to the power of x and y equals log of x look like this. And here's a diagram from your textbook. So here's the red one here is one you should be familiar with. This is y equals 10 to the x. And so when x is 0, y is 1. When x is 1, y is 10. When x is 2, y is 100, and we're not going to fit that on this graph. The logarithmic function just takes each of those points and switches the x and y. So instead of 0, 1, I have 1, 0. Instead of 1, 10, I have 10, 1. Also, don't forget that inverses are basically the one function reflected over the line y equals x. So let me just sketch that in here. This is the line y equals x. And if two functions are inverses of each other, then they're going to be reflections. So you can see this point here is a reflection of this one here. This one is a reflection of that. And if we went up to 100, that would be the same as well. And I think I said this here in the notes. Notice that the x and y coordinates are switched and that the graph of the log function is the graph of the exponential function, which is reflected over that perfectly diagonal line y equals x. Also notice that the x-axis is an asymptote for the exponential function. We talked about that previously. That's this curve right here. And the x-axis is an asymptote. And that for the logarithmic function, the y-axis is an asymptote. So let's take a look at a graph, and let's go ahead and graph one here. So here we need to graph y equals log base 3 of x. And you actually can't do this in your calculator. We're going to have to do this by hand. But I know that the inverse of y equals log base 3 of x is y equals 3 to the x. And I can graph that by making some points. So I'm actually going to find some points for the inverse and then just flip them and graph those points. So for y equals 3 to the x, I'm going to do -2, which is going to give me 1/9, -1, which gives me 1/3, 0, 1, 1, 3, and 2, 9. Now, my table of values for y equals log base 3 of x is going to be just those values switched. So when x is 1/9, y is -2. When x is 1/3, y is -1, 1, 0, 3, 1, 9, 2. And let's go ahead and graph those points. So 1/9, -2, it's impossible to graph 1/9, but it's going to be something like that. 1/3, -1, 1, 0, 3, 1, and 9, 2. So actually part of this kind of looks, this part of it kind of looks like the square root function that we graphed in the last chapter, but then we have this part which approaches the y-axis but never touches it. So there's my graph of y equals log base 3 of x. Okay, you'll notice that its domain is x is greater than 0. It never hits the y-axis, so x is never equal to 0 and it never goes into the negative range. The range is all real numbers because it can keep going higher up here and it can keep going lower in the y values here. It has no y-intercept because it's never going to cross the y-axis, but it does have an x-intercept at x equals 1. And it has a vertical asymptote at x equals 0, which is the y-axis. Okay, and that's how you would graph a logarithmic function. And the last thing we're going to take a look at here is transformations. Actually, I shouldn't have said translations. I should have said transformations there. Sorry about that. It can be transformed. So just as we saw with a lot of other functions that we've dealt with, we can also do transformations on the parent logarithmic function, which is y equals log base b of x. So we can do stretches and compressions and reflections, and that's going to be reflected here in an A in front of log base b of x. We can also do horizontal and vertical translations, and again you're going to see this familiar x minus h on the inside of the function and this plus k outside of the function. And then if you put all of the transformations together, you're going to get y equals a times log base b of x minus h plus k. Let's do one example together here. So we want to describe how the graph of y equals log base 2 of x minus 3 plus 4 compares to the graph of its parent function. Then we're going to graph the function, identify the domain, range, y-intercept, and the asymptote. So looking at this, my h is equal to 3, so that means I'm going to move right 3, and my k is equal to 4, so that means I'm going to move up 4. So that's how it's going to compare to the graph of the parent function. Let's go ahead and graph the parent function, and then we'll just move it right 3 and up 4. So my parent function is y equals log base 2 of x, and that's going to be the inverse of y equals 2 to the x. So I'll make a table of values for that, which you should be pretty familiar with now. Negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, 2, 4, and I'm going to go out one more, 3, 9. And then the parent function for y equals log base 2 of x is going to be those x's and y's switched. 1, 0, 2, 1, 4, 2, and 9, 3. So let's go ahead and graph those points. So 1/4, negative 2. Again, it's hard to get exactly 1/4, but let's do close. Negative 1/2, negative 1, 0, 1, or I'm sorry, 1, 0, 2, 1, 4, 2, and 9, 3. So that's the graph of y equals log base 2 of x. Now I'm going to take each one of those points and move it right 3 and up 4. And to do that, I think I'll change my color here. I'll go ahead and do that in red. So starting with my first point here, I will go right 3. 1, 2, 3, 1, 2, 3, 4. And then 1, 2, 3, 1, 2, 3, 4. 3, 4. Did I do that one? 3, 4, 3, 4, and this last one won't fit, so we're not going to worry about it. So draw that curve there, and now you can see that this line where my asymptote is actually moved 3 to the right as well. So I'll go, whoops, wait, that's not the one I graphed. What I graphed was this here. I'll box this in red so that stands out. Okay. The other thing I have here, and I'm going to go ahead and go back to my black, and I like to draw this. This line right here is going to be my asymptote. And that's the line x equals 3. So let's identify our domain and range. The domain is x is greater than 3. Notice that I don't have any points that are going to the left of my asymptote x equals 3. My range again is all real numbers. Okay, my y-intercept, I have none. It does not cross the y-axis. Oops, I write none instead. And I have a vertical asymptote. At the line x equals 3. So I apologize, this was a very long video, but there was a lot of stuff in this lesson. First time we took a look at logarithms, we saw that they are actually the inverse of the exponential function y equals b to the x. The inverse of that is y equals log base b of x. We looked at how to write something, go from exponential form to logarithmic form and how to solve equations that way. We looked at the graph of the basic logarithmic function. We also talked a little bit about common logs, and then we talked about how to do transformations of the parent logarithmic function.